So this is a sample of a problem that gets missed often on our final. So we're going to go ahead and go over it. We're going to draw our interaction diagram as well as our force diagram. So our interaction is there is the elephant and the ball. Okay, the ball and the floor also have an interaction. And the circus elephant has a gravitational, and the ball also has a gravity. Let's just go ahead and make a key really quick. So E for Earth. Okay, C for circus elephant. B for ball. And G for ground. Okay, so now we're just going to go over to the side and make the force diagram for the ball. Okay, so it's acting on the ball, so force diagram for the ball. We have our B, we have the force of gravity on the ball from the earth. Now this 13,000, so this 13,000 right here is for the elephant. The ball itself weighs 1,400. So the ball is 1,400 newtons. And the elephant has a downward force on the ball. So elephant is pushing the ball down at 13,000 newtons. And so that means that the floor, or the ground, is pushing up on the ball, and it is happening at 1,400 plus 13,000, which is going to be 14,400 newtons. Okay. All right, so for this problem, this is asking how much the force is on you when you're pushing the boulder up. So what we have to remember here is that this is an interaction. This right here, where you and the boulder are pushing on each other, is one interaction. And Newton's third law states that for every action there is an equal and opposite reaction, right? So this, you are being pushed in this direction by the boulder, and the boulder is being pushed in the opposite direction. Okay. The force that the boulder exerts on you, so it'll be a normal force on you, so we'll call it person by the boulder, is going to be equal to whatever you are doing to the boulder. And it looks like it's 250 newtons, so then this will also be 250 newtons. All right, this is a problem that we frequently miss because we get confused by this question. What is the Newton's third law pair between the box and the earth? And we don't normally draw a force diagram for the earth, but what we want you to understand is that the box and the earth are a Newton's third law pair. So what we're going to be looking at is this interaction. Okay, so the box and the table have a normal interaction, but then we have the earth. Okay, so we're actually not looking at the box and the table. I'm sorry about that. We're looking at the box and the earth, which is a gravitational or a force of gravity. So we have the box. When we all do this first, right? The weight of the box, or the force of gravity. But then what we don't do as often is draw a force diagram for the earth. Okay? And the earth is being pulled up by the box using the force of gravity. Okay, so we know that they're going to be equal to each other, but we just don't know how much. And that's Newton's third law pair. Okay, this is a problem that we went over in class, but I think a lot of us were kind of confused by it. And so Edson here weighs 75, or has a mass of 75 kilograms. Elima over here has a mass of 55 kilograms. And they're standing on ice, so frictionless. Okay, so I want you to remember that. Edson pushes Elima, who accelerates at 7 meters per second per second. What is Edson's acceleration? So we don't know what his acceleration is. Okay, it's a question. So the first thing you'd want to do is draw a force diagram, or like just kind of draw the general idea. So we have Edson here, who has a force of gravity. Okay, force of gravity on Edson done by the Earth. And then he also has a normal force on Edson from the ice. All right. And Elima is pushing him in the left direction. So we have Edson who's being pushed by Elima. Oh, I guess the ice, we'll call the ice floor. Okay. All right. And then Elima, there's a force of gravity on Elima from the Earth. And she is being held up by the floor. So force, normal force on Elima by the floor. And Edson is pushing her to the right. So there is a normal force on Elima from Edson. Now we got to try and find out what their net force is, right? So it's unbalanced, but these cancel out because they're the same. And so whatever's left over is going to be the net force. So this is the Newton's third law pair, and it's happening right here. All right, so Elima's net force is going to be equal to Edson's net force. So if we find out what the net force is for Elima, then we can find out his too. So the net force is going to be mass times acceleration. We have 55 kilograms times 7 meters per second is going to be 385 newtons. Okay, this is Elima's. All right, now Edson, which I'm going to write down here, his net force is also going to be 385 newtons because of Newton's third law pair. We know his mass is 75 kilograms from the problem, okay? It's given to us, but we don't know his acceleration, so we'll leave that blank. Now we're just going to do simple algebra where, we'll just divide by 75 kilograms, so that cancels out. And we're left with an acceleration, and we are going to take our calculator, go 385 divided by 75, and it's going to be about 5.1 meters per second per second. All right, and so that's it. Please make sure to bring all of these materials to the finals, as well as, so you should also bring pencils, pens, erasers, plus calculators. There won't be any extras, so make sure to bring your own stuff, okay? If you have any questions, as always, you can make sure to email me at mmedrano@shcp.edu. All right, good luck, everybody.